What is viscosity? Well, let's start by comparing two different liquids. You have water, which can move very quickly and very easily, and you have honey, which can move more slowly. And if you spill it, you have some time before you need to clean it up. When we look at the molecules of both these substances, you can see that water holds on to each other like they have sweaty hands, whereas honey, they're holding on for dear life until you add some heat to them. Then they begin to move faster and break apart more easily. Viscosity being the fluid's resistance to motion, there are many things that can affect it. Obviously, temperature is one of them. Let's say, for example, you're trying to get some syrup onto your pancakes, but the syrup won't come out. If you put the syrup bottle in the microwave and heat it up, the syrup will move more easily. It can also get easier to pour a substance when you add water to it, like when you're at the bottom of your chocolate syrup bottle and you want some chocolate milk. You might pour some milk right into the bottle and shake it up to make it easier to get the chocolate syrup out. We would say these examples make a substance less viscous or less resistant to motion. So what does viscosity have to do with motion or the acceleration of an object? Here we have a large graduated cylinder filled with quite a bit of honey, and we have a small ball bearing. When we drop the ball bearing into the fluid, we can see that it moves at a constant rate. This is called terminal velocity, and this happens because the forces acting on the ball bearing are balanced. I can demonstrate this with a diagram. Here we have weight or gravity pulling down, then we have drag and viscosity pulling up, and at an equal force to the drag and viscosity, we have upthrust and buoyancy. So the force of gravity is equal to the combined force of the drag and the upthrust, equal and opposite. Therefore, zero. Therefore, constant. We can test this further. Theoretically, if we had a supergiant tower filled with layering fluids of different viscosities and we dropped a ball bearing into it, we should see the velocity or the acceleration of the ball change as it passes through each fluid. This is because each fluid is exerting a different viscous force. You can see by changing the viscosity or the resistance of the fluid, we can affect the overall acceleration of the ball bearing. You can also do this with ball bearings of different masses to observe how mass affects this relationship. So how do we measure this? We have to gather several measurements in order to calculate the terminal velocity. You start by determining the mass, diameter, and volume of the sphere that you're using. The mass is determined using a scale, the diameter can be determined using a digital caliper or ruler, and the volume of the sphere is determined by the following formula. Once you've determined the mass, diameter, and volume of the sphere, now you have to determine the mass and volume of the fluid that you're using. Again, we used a digital scale to determine mass and a graduated cylinder to determine volume. When we measure the time the ball bearing takes to travel through the graduated cylinder, we will record the time at different positions throughout the cylinder. Once you've collected several time trials of this test, you're going to plug all this information into a fancy formula to calculate the terminal velocity. So if you had multiple positions marked on a large graduated cylinder and you collected the time the ball bearing reached each position and then plotted them onto a graph, you would see the change in position, the y-axis, over time, the x-axis, is approximately the same for every point on the graph. We describe this as a constant change. Overall, there are balanced forces at work in this experiment, and it is a cool opportunity to see constant motion and apply all of Newton's laws of motion. So why do we care? Why does this matter in the real world? These experiments are simple ways to observe the fluid force of viscosity, which is its own scientific field, rheology. Rheology is essentially how fluids deform or change shape under different types of stress or force. The rheologists I know are more focused on exploring the rheology of magma. This could help determine the type of eruption a volcano could have. For example, I would want to know, is the volcano just going to rush lava, or is there gas leaking through bubbles within the magma that are going to cause it to explode in a more solid-like state of matter? They're working to figure this out.